Picking up where we left off, question number 27, doing more dimensional analysis. So we want to convert milligrams to grams. So our conversion factor is 1 milligram is 10 to the minus 3 grams. So I'm going to start with my given information, 5315 milligrams. And I'm going to use a conversion factor that has milligrams on the bottom. So 10 to the minus 3 grams on top, 1 milligram on the bottom. So our milligrams will cancel. And our final answer should come out to be 5.315 grams. So that would be our first answer right there. So how many inches are there in 14.35 centimeters? So I want to remind you all, I haven't mentioned this in a while, but just as a reminder, what you should be doing for your own practice is to pause whenever we get to a new problem. Give this video a pause, work the problem yourself, then press play again and see if you've worked it and gotten the same answer in the same way that I did. So, but to continue on, so we've got our conversion factor given to us right here in our problem. 1 inch equals exactly 2.54 centimeters. So we'll start with our given information, 14.35 centimeters. And I'm going to write my conversion factor to put centimeters on the bottom. So inches will go on top, centimeters on the bottom. So I should get, when I punch that into the calculator, what it gives me back is a big old number, 5.649606. Right? But I need to take into account my sig figs. So this is a definition. So it is considered to have infinite significant digits. So it's a division problem. So I go with the fewest number of sig figs in my problem. So 4 is a far cry from infinite. So I'm going to stop at my 4th significant digit, which is this 9. And I'm going to look 1 digit to the right to decide whether to round it up or round it down. So since it's a 6, I'm going to round it up. That becomes a 0. This becomes a 5. So my final answer here should be 5.650 inches. And it gets a little tricky when you're dealing with 9s, but 5.650 is our correct answer. Right, so we have a commercial greenhouse requiring an average of 75 gallons of water per day. What is this in liters per year? So again, I want to encourage you to pause the video, see if you can work out the problem yourself, and then come back and see how we did it. So our conversions, just as a a quick reminder, so we can write these either way. So 1 gallon, 3.79 liters. That's our first conversion that we're given here. Or 3.79 liters over 1 gallon. I can use that however I need to in my problem. Those are your two options. The other conversion is 1 year, 365 days, or 365 days over 1 year. All right, so I'm going to start with my given information, which is 75 gallons per day. And I'm going to work this problem in one continuous thing. As a reminder, you can work this one step at a time. You don't have to do this as one long continuous chain. But in the interest of efficiency, I'm going to go ahead and work this as one continuous chain. Now I could deal with the gallons or the days, really doesn't matter which one I deal with first. Both of them have to be converted. But I'm simply going to choose to go with the days first. So right now I've got days on the bottom in my given information. So I'm going to write a conversion factor that has days on the top, so they're on opposite sides of the fraction bar. Right, so my days will cancel. So if I stopped right here, I would have an answer that is gallons per year. So I'm going to do another conversion because I want to change the gallons into liters. So right now in my given information, gallons are on top. So I'm going to write a conversion factor that puts gallons on the bottom to make gallons go away. All right, so the gallons will cancel out now. So the only units that are left are the liters per year, which is what I'm looking for. So we end up with an answer to the correct significant digits of 1.0 times 10 to the 5 liters per year. And it's two significant figures because I have two significant figures in my original information, and my conversion factors are both definitions, so they both have infinite significant digits. All right, finally a new concept, right? So, but what's nice about this is because we have a fraction, I can use density as a conversion factor, just like everything else we've done. Right? Mass divided by volume, mass per volume. Anytime you have something per something, you can use it as a conversion factor. All right, so question 30. Give this a pause, see if you can figure it out, and then come back. So I said we can use our density as a conversion factor. So this 792 kilograms per cubic meter, right? Don't be fooled because it's written side by side. It's the same thing as saying 792 kilograms over cubic meters. That means the same thing. Or cubic meters over 792 kilograms. Right? Doesn't this look just like the previous problems that we were working? Right? So I'm going to start with my given information. If 792 kilograms per cubic meter is a conversion factor, then that means that my given information is right here, this 0.3 cubic meters. So now I have my conversion factors that I can choose from, and I'm going to put cubic meters on the bottom to make the cubic meters go away. Okay, just like all the previous problems. I don't have to do anything algebraically, and I hope most of you are breathing a sigh of relief from that. No algebra needed. Everything's through conversion factors. You just set these conversion factors up correctly, and all of the work will be done for you. So our cubic meters will cancel out because they're on opposite sides of the fraction bar. And so we should get an answer of 2.38 times 10 to the 2 kilograms. All right, question 31. The density of elemental bromine is 3.1 grams per milliliter. What is the mass of 15 milliliters of bromine? Give this a pause, come back and see how you did. So our conversion factors, density is a conversion factor. Anything per something, grams per milliliter, is a conversion factor. So I can write my relationships, or milliliters per 3.1 grams. Right? So I'm dealing with milliliters as my given information. So everything works out just fine. So I'm going to start with that because my given information is the same units as what are in the density. Okay? So I'm going to write a conversion factor that puts milliliters on the bottom. So I'm going to choose the one that looks like this. My milliliters will cancel, and we should get an answer that is 46.5 grams. So question 32. The density of an aluminum block is 2.7 grams per cubic centimeter. Okay, so you should recognize by now, we've done a couple of these problems, that this is now a conversion factor. Right? Now recognize that your given information, the units don't match. Okay, I have kilograms in the given information and grams in the density. So I have to convert my kilograms first before I can use my conversion factor. So hopefully we've done enough practice by now that your memory is serving you well, and you know that there are 10 to the 3 grams in 1 kilogram. So I'm going to go ahead and skip over writing all of that out and just go ahead and do the conversion. So I have 4.38 times 10 to the 3 grams. So now that my given information here has the same units as my density, I can now use my density as simply as a conversion factor. 4.38 times 10 to the 3 grams. I'm going to use a conversion factor that puts grams on the bottom. So cubic centimeters go on top and 2.7 grams go on the bottom. That's my density. So my grams will go away. And we're going to divide by 2.7 because it's on the bottom of our conversion factor, so we should get an answer that is 1.62 times 10 to the 3 cubic centimeters, which is the same thing as 1,620 cubic centimeters. Now, density determines whether something will float or sink. Okay, and those are the words that are on this slide. But the point is that if something has a lower density than, for example, water, it will float. So if water, the density of water is 1 gram per milliliter, and the density of this particular block, probably a wooden block, is 0.4 grams per milliliter, it will float. So as long as the density of whatever you're looking at is less than the liquid that it's in, it will float. If the density is more than the liquid you're in, the thing will sink. So let's take a look at question 33 here. So it's a watertight crate measuring 2 meters by 1.5 meters by 3 meters is filled with freight. The mass of the filled crate is 1,800 kilograms. What is the density of the crate in kilograms per cubic meter? So whenever you need to find density, density equals mass divided by volume. Okay, so we're given a mass of 1,800 kilograms. That's given right here in the problem. And then we need to find the volume of this crate. Remember, volume is length times width times height, and that's given to us right up here in our problem. So 2 meters times 1.5 meters times 3 meters gives us a volume of 9 cubic meters. So density equals 1,800 kilograms divided by 9 cubic meters. So when we do that bit of math, we get 200 kilograms per cubic meter. So the crate in the last question had a density of about 200 kilograms per cubic meter, so we were correct. If this crate falls overboard and falls in, let's say, water, will it float? Now the density of water is 1,000 kilograms per cubic meter. So our object, our crate, is 200 kilograms per cubic meter. If the object is less than the thing that it's in, so if the density of the object is less than the density of water, it will float. So the answer here is yes. Okay, so we've got a couple more questions involving density here. So tell whether the following would float or sink in water. A rectangular block with the following measurements with a mass of 0.583 kilograms. All right, so water, so we said in the previous question here that water has a density of 1,000 kilograms per cubic meter. So we can go through a process of conversion, but it would be easier for me to just tell you the density of water in different units is 1 gram per cubic centimeter. Okay, 1,000 kilograms per cubic meter or 1 gram per cubic centimeter. And it's all about the conversions. Trust me, this works. Okay, so I have my centimeters in the problem to determine the volume of our block. But our kilograms is not going to work with our density. So I need to first convert my kilograms to grams. All right, so we have 0.583 kilograms, and we have 10 to the 3 grams per kilogram. The kilograms will cancel, and so we get an answer of 583 grams. Our volume is 5 centimeters times 4 centimeters times 2 centimeters gives us a volume of 40 cubic centimeters. So our density of the block, or whatever it is mass divided by volume. So the density is 583 grams divided by 40 cubic centimeters gives us 14.5 grams per cubic centimeter. So what do you think? So if the density of water is 1 gram per cubic centimeter and our object is 14 grams per cubic centimeter, it's going to sink. Okay, it's very important to make sure that your units match. All right, so 35B here, tell whether the following would float or sink. A diving tank with a volume of 0.4 cubic feet is filled with air. The tank, the filled tank weighs 35 pounds. Okay, so we need to figure out whether this thing has a density that is greater than water. Right, so we need to find the density in terms of grams per cubic centimeter. okay, because that's what we know of water. Right? So we're going to convert the mass first. So we have these conversions that are given to us in the problem. Right? So 454 grams in 1 pound. So we have a mass of 35 pounds. And it's 454 grams per pound for 1 lb. So our mass comes out to be 1.589 times 10 to the 4 grams. Our volume, we have 0.4 cubic feet. Our conversion there, we're going to put cubic feet on the bottom. So our volume is 1.12 times 10 to the 4 cubic centimeters. So our density is mass divided by volume. So I'm going to say 1.589 times 10 to the 4 grams. And we're sort of running out of room here. 1.12 times 10 to the 4 cubic centimeters for our volume, mass divided by volume. So our density comes out to be 1.4 grams per cubic centimeter. Now remember, water is 1 gram per cubic centimeter, and our object is 1.4. So it's going to sink. And this example B here, instead of converting to grams per cubic centimeter, converted everything into pounds per cubic foot. That works too. The result is the same. The object will sink. I'm going to stop this video right here, and when we come back, we're going to talk about temperature conversions.